Now let's look at a concept known as empirical formulas. And empirical formulas are the smallest whole number ratio of atoms to one another in a chemical formula. Now, ionic compounds typically are already written as empirical formulas because we're always looking for the smallest whole number ratio of cation to anion. However, molecular compounds often are not written in empirical formulas because they're given an actual number of atoms in a given molecule. So let's look at how this works. Let's look at hydrogen peroxide. Here its molecular formula is H2O2. Hydrogen peroxide always has 2 oxygen atoms and 2 hydrogen atoms. There's a common factor here of 2, and when we divide it out, we get our empirical formula, HO. Let's look at benzene. The molecular formula is C6H6. In a benzene molecule, there are 6 carbon atoms and 6 hydrogen atoms. There's a common factor here of 6, and when we divide that out, our empirical formula is CH. Glucose always has 6 carbon atoms, the black, 12 hydrogen atoms, the white, and 6 oxygen atoms. There's a common factor between 6, 12, and 6 of 6. When we divide that out, we get 6H2O. This is the empirical formula. So see if you can determine the empirical formula of this compound benzopyrene C20H12. So to determine the empirical formula, we're going to look at the largest number that goes in evenly into 20 and 12, otherwise known as the greatest common factor. And the largest number that's going to go into both 20 and 12 is 4. When I divide 20 by 4, I get 5, and when I divide 12 by 4, I get 3. So here's our empirical formula, C5H3. Notice that when you get down to the empirical formula, we'll look back here, the subscripts have no common factor besides 1. So here's 1, 1, 2, and 1. You could start out by reducing this by 2, dividing 2 into each of these, and then you get C3H6O3, and you'd have to take it one more step so that each subscript has no common factor besides 1. Okay, so now that you understand what an empirical formula is, we're going to look at how to calculate an empirical formula from given data. And what you're going to be doing is following these basic steps here. If you are given elemental percentages, what you need to do is convert those to grams, and we'll see that's very simple to do. However, sometimes the problem gives you elemental composition in grams. If they already do that, then skip to step 2. Once you have your elemental composition in grams, then you want to convert your grams to moles. And we do that by dividing by the molar mass of each element. This is the value on the periodic table. Next, we're going to write a pseudo formula using the moles that we calculated from step 2 as our subscripts. And we want to follow the order that we learned in chapter 5 in ordering our elements. Once we have this written out, we identify which subscript is the smallest, and we divide all the other numbers by it. The numbers that we get may be whole numbers. If they are, then we're done. If we have a number that has some number here and then it's 0.5, we've got to multiply all our values to get a whole number. So if we have 0.5, we multiply by 2. If we have 0.3 or 0.67, we multiply by 3. So what the heck do I mean by this? Well, let's look at an actual example, and hopefully it'll make some sense. So here's an example. A laboratory analysis of aspirin determined the following mass percent composition. Find the empirical formula. So this would be a typical question. This is all you would be given, and based on this, you're going to be able to find the empirical formula. Now, mass percentages, due to the law of constant composition, are always the same. If I have 10 grams of aspirin, it's going to be 60% carbon. If I have 1,000,000 grams of this aspirin, it's still going to be 60% carbon. So whenever we are given percentages, we always assume we have 100 grams because the amount doesn't matter, and it's so easy in this case to get our percentages to mass. If I have 100 grams, then 60% of it is 60 grams. If I have 4.48% of it, if 4.48% of 100 grams is hydrogen, then there's 4.48 grams. So we always just change our percentages directly to grams, maintaining our sig figs. Okay, so that was step 1. Step 2, well, they're putting this in here. This is how our formula is going to look. We're going to have carbon first, then hydrogen, then oxygen, and we're trying to figure out what these subscripts are, the empirical formula. So step 2 is to convert our grams that we figured out from step 1 into moles. And we do that by dividing our mass by the molar mass. And these are values that we find on our periodic table. So it's definitely worthwhile to take the time to write this down. 1 mole of carbon, 12.01 grams, etc. Okay, then we take our masses and we convert them to moles by dividing by the molar mass. And here they just take it to the number of sig figs that your value gave you. I like to take it one past and then round. I'm hoping that's what they did there. So we have 4 sig figs, 4 sig figs, 3 sig figs, 3 sig figs, 4 sig figs, 4 sig figs. So we just completed step 2, converting our grams to moles. Then we write our pseudo formula using the moles that we determined as our subscripts. So if I look previously, we got 4.996 moles of carbon, so that's my new subscript. 4.44 moles of hydrogen, my new subscript. 2.221 moles of oxygen, my new subscript. Then the next step is to identify the smallest value, which would be this one, and divide it into all the other values, including itself. So when we divide this into itself, we're going to get 1. That's going to be the new subscript. So here we are dividing this value into all the other values, and this is the answer that we get. C 2.25, H2, and O1. Now if these were all whole numbers, we would stop right now. And let me just say that if you have something in the tens position that is 9, you can round up, or 1, you can round down. Certainly if it's 0. You may not get completely whole numbers. You may get something like 1.01. You can round that to 1, or 1.99. You can round that to 2. But if you get 2.25, then that counts as a fourth. And what we have to do is make it a whole number. 2.25 is the same as 2 1/4, and to make a fourth a whole number, we've got to multiply it by 4. So when I multiply these values by 4, we get C9, H8, O4. So we can see that our subscripts have no common factor, and this is an empirical formula. How would we know if this is right or not? Well, it's kind of hard to say, because you can get numbers as high as 20 in some of these compounds. But one checkpoint is whether these values have a common factor or not. If your values do have a common factor, then it's not an empirical formula, and if they don't, then that's a good indication that you have actually calculated the empirical formula. So let's go back to our steps. This last step is after we divide all our moles by the smallest number of moles, and we get an answer that's not a whole number, like we did 2.25, then we've got to multiply it by some number, and we multiply all the subscripts by the same number to get it to be a whole number. So when we do step 4, divide by the smallest numbers of moles, and we get a value that has a 0.5 in it, then we multiply all the subscripts by 2. If we get a value that has a 0.33 or a 0.67, we multiply all the values by 3. And if we get something like 0.25, we multiply by 4. Those are the 3 most common scenarios.